No, makes sense. It's like, none, I knew. Going to this. It all depends on how you want to fix. For things, it's definitely or yeah. So I think the case is said. Right. Yeah. It was always meant to be. It was always meant to be in the Seahawks and with their advantages. At least, the back of the becoming subsiding. So you send them. You let go of your starting quarterback. Yeah. Well, I think you just one. Pretty change your call. Last. That's a just better. Greatest percent on the wow, right? I see. What do you think of that bonus? Do you know? So like here's the report. Exactly. I see one. So you get to regular streaming, watch them push you over. It's fun. They don't have murder Patriots. Patriots pretty good Wednesday inside 35 seconds. It's hard to say because I don't know, that's some games if you're going defense and pulling forward. I've been seeing that's most every time. There's no way. You're not being that smart. Or the Giants. Sign, I mean, for just go on. Yeah, that's true. Engineering department also. They screwed this week. They said about. Then we got this was a future. And then we got to do that. Oh, the aeroplanes. Yeah, so the line. So. It was so I can
Good. How are you guys? Another day? It's only week 2. You can't be like, you gotta wait until like week 5 to feel like that. All right, it's 4 o'clock. Let's go and get started. All right, good afternoon, everyone. How's everyone doing? Good, hanging in there. Just another day. All right. Well, it's another Monday, so it's time for, well, it's actually technically our first Monday because last Monday we missed because of the holiday. So today we are going to be finishing the lecture that we started last Wednesday. So we'll be doing a review of fluids. I don't want to spend too much time on it, so I am going to skip some stuff or just kind of, go through it fairly quickly because I do want to get to finite differences. So I'm hoping that, the first half of class today will be on fluids and the second half will be on finite differences. Okay. All right. So announcements. So I think I answered everyone that emailed me. So I kind of spent the entire morning and afternoon emailing just because most people kind of wait until Sunday to do it, which is fine. But if you haven't sent me your introduction email, please make sure to do that just so you can get credit for it. It is late at this point, but you definitely want to get that in before too many days pass. We're not really at a point yet where we can do a homework set since we just only had our first day. But I do expect the first problem set, the first homework is going to be posted later this week for this class. So just keep an eye on it. Okay. All right. Yeah, it's not too much. We've only had one lecture before this. Any questions I can answer before we get started? Okay. All right. So let's go ahead and continue with our review of fluids. So last Wednesday, we started reviewing fluids. And so we just went over very basic concepts in terms of, what a velocity field is, what a pressure field is. And we went over just the basic material properties for fluids too, which are viscosity and density. So today I want to start with reviewing one of the core concepts from 333, which is Reynolds transport theorem. Okay. So usually within the context of fluid mechanics, Reynolds transport theorem comes up within the subject of finite, control volumes, right? And so usually, when you want to do an analysis on a fluid system, usually, let's say that we have, pipe system like this, right? Right. So you might have flow coming in, flow coming out, right? And so probably what you guys are accustomed to from fluids is, let's say that if we wanted to analyze this from a conservation of mass, conservation of momentum principle, right? We would draw a control volume around this entire geometry. So we draw something like this. Right, so this here in pink, this would be our control volume. Right, and then to do the analysis, we would apply Reynolds transport theorem to this control volume. Okay. So this concept is actually very important for CFD because a lot of the theory that we're going to be developing, in particular about finite volumes, I almost said finite volumes instead of control volumes, is kind of based around this idea of Reynolds transport theorem. So it's important to go over. Okay. Okay. So Reynolds transport theorem is an integral theorem. So it's it's expressed using integrals. Okay. And I think the most general form of it is given by the following. Okay. So for a general transport quantity, okay, and let's call that transport quantity capital B. Okay. So B is just a general quantity, but if you remember from fluids, we can apply Reynolds transport to basically anything that's conserved. So this B here could represent mass. It can represent momentum. It can represent energy. I think those are probably the most common. You can also apply Reynolds transport theorem to angular momentum as well, but that B is just any kind of conserved quantity. Okay. Okay. So for any conserved quantity and a control volume, so those are kind of the two requirements for Reynolds transport theorem, is that you have those two things. Mathematically, we can express it like this. Okay, so on the left-hand side, we actually have a derivative. So we have dB dt is equal to partial t of the integral of rho lowercase b dv plus integral across the surface of rho b velocity field dot product with the normal vector dA. So for this class for CFD, the mathematical details of this are not as important. We're not going to be doing control volume problems in this class. What's actually more important is the conceptual understanding of what this equation represents, especially with respect to a fixed volume of fluid within that we define in our control volume. Okay. So what I'm going to do here is that for each of these three terms here, I'm going to basically define what these mean. And then we'll kind of put that within the context of what that actually means for CFD. Okay, so this first term right here, this dBdt, this is what we often call the production term. Okay. Production usually means or has the implication of producing new amounts of capital B, but you can also do the opposite too. So B could also be destroyed as well. So this is the production / destruction term. Okay. So what that term represents there is just any way for our quantity B to be created or destroyed within the control line. Okay. Okay, so that's the first term. Second term, this is what we call the accumulation term. Which again, accumulation kind of has a positive connotation where something is building up, but you can also have the opposite to happen as well. So the opposite of accumulation is depletion. Okay. So that's the accumulation / depletion term. And what this term here represents is the ability for B to collect or deplete within the control line. Okay, so not necessarily being produced or destroyed. It's more accumulating or depleting. So there is a difference between those two. All right, and then we have the last term. The last term here arguably is the most important for what we're going to be doing for CFP. Okay. All right, so this last term here is often called the flux term. Or I think a bit more descriptive name for it would be the inflow and outflow term. And so what that last term there represents, it represents the ability for B to be carried into the control volume or carried out of the control volume with the fluid. All right. So Reynolds transport theorem is it's a great concept because I think mathematically it looks intimidating because you have all these integrals and derivatives and going on, but conceptually it's actually a very simple concept to really understand where whenever you have a control volume, whenever you have a fixed region in space that you're considering, basically this is saying that what goes into the control volume either will collect into the control volume or not, right? So the analogy that I like to give with Reynolds transport theorem is think of a bank account, right? Okay. So this analogy is going to look a little bit weird because I think typically with the bank account you think of your balance first, but I want things to kind of line up exactly with the Reynolds transport theorem that I'm talking about. Okay. Okay. So one thing your bank account can do, let's say that you have your money in like a money market or something like that, is that your bank account can produce interest, right? Right. And so if you have a certain amount of money in your bank account, then the bank will basically pay you money for keeping money in there based on what the bank invests money in and the returns that they get, right? And so let's say you have $100 in your bank account, and let's say that the savings account that you have has a 3% annual return. And so what that means is that just by nature of that $100 being there, $3 gets automatically generated within that bank account. Okay? And so at least from your perspective, right, as a user, your money is being spontaneously created within the bank account just by nature of the bank account existing. Okay. Okay. So thematically and you know, that's exactly kind of what the production and the destruction term represents. Is that, ways for our quantity B to either be spontaneously created or spontaneously destroyed. Okay. All right, next we have the accumulation and depletion term here. So the kind of the analogy in your bank account is this is analogous to your balance. Okay. So that shows how much money that you currently have in the bank account. Okay. Right. So I think that one's pretty self-explanatory. Right. So the balance just represents how much money you've accumulated, over time in the bank account. Okay. All right, and then the analogy for the flux term is going to be any deposits or withdrawals that you make from the bank account. Right? So if you put money into the bank account, your balance is going to go up. If you take away money from the bank account, your balance is going to go down. Okay. Right. So if we kind of rearrange this a little bit, it becomes a little bit more clear. So, I think the way that people typically think of their bank account is the balance is on one side of the equation, and then everything else that affects the balance is on the other. So, we can move this balance and withdrawals to the opposite side. Okay. And then what you have is balance is equal to the interest generated plus the deposits minus the withdrawals. Okay. So I think that's typically how people think of their. Okay. Right. So this analogy here is pretty good, and kind of illustrates what each term here represents in the Reynolds transport theorem. And so the only tricky part is that, taking the same idea of a bank account and then applying it to a conserved quantity, right? Right. So we can apply it to mass, momentum, and energy. So I'll do that kind of in the next example. But, I wanted to kind of get through that analogy first to kind of illustrate what this kind of represents. Okay. All right. Any questions on this so far? Okay, good. Okay. So let's see what this would look like when we apply it to a conserved quantity. And I'll do two, actually, just so you can kind of see. Okay, so let's see what the Reynolds transport theorem would look like when you apply it to mass. Okay. Okay. So let's go through each term kind of individually and kind of see what it would look like. Okay. Okay, so let's go through production first. And so, is there any way for mass to be spontaneously produced or destroyed? No, there's not. That's kind of the fundamental conservation theory of mass, right? So the production term for conservation of mass is actually zero. So no matter what you do, there's no way for mass to be created or destroyed. It may change states, but it can never be fully destroyed, okay, or produced. Okay. And so if we do that, then everything else kind of falls in place from there. So Reynolds transport theorem, right? If we say that the dB dt term is equal to zero, and we kind of line everything else up as it is, right? We get 0 is equal to partial t of integral of the volume density times volume plus flux integral of rho v dot n hat dA. So Reynolds transport theorem applied to mass is actually quite simple because, basically what we say is that, the mass is already here, right? So we already have density as part of the equation. And so the way that we obtain this form is we set little b is equal to 1 for mass. Okay. So since mass cannot be created or destroyed, right? Since that production term is zero, what this is saying is that the only way for fluid mass to accumulate or deplete within the control volume is for there to be an imbalance of inflow and outflow from the control volume. Right. So that's kind of a lot of words that kind of say something that's pretty straightforward, right? And so if you think of fluid as like people, right? So the only way for the capacity of this room to increase is for people to come into the room. And the only way for this room to become empty is people leave the room, right? If you think of that door as kind of our flux, so that's our portal, right? We have an inflow when people come in, an outflow when people go out, right? And that's the only way for this room to accumulate or deplete people. Okay? Now in CFD, we're going to take this a step further. And so in CFD, our control volumes are going to become our mesh elements basically. So these little finite volumes, these little triangles in our geometry, right? And so when we do CFD, we're going to make the further assumption where, we're going to assume that there's going to be no accumulation or depletion of fluid within the control volume, right? Basically, we're not going to have the way that we call in CFD is we're not going to have multi-phase flow. So we're going to assume the fluid is kind of homogeneous throughout, right? And so if we assume that, then our accumulation is gone as well, okay? And so then what you're left with here is that you're only left with the inflow and outflow terms. And then when you eliminate all the other terms, basically what you're saying is that the amount of fluid coming into your control volume or coming into your finite volume has to equal the amount of flow going out. Okay. And that's an idea that we're going to leverage quite a bit when we start going over finite volume here. Okay. But we'll definitely cross that bridge when we get there. But for now, I think it's fine to just, think about Reynolds transport theorem, think of the analogy, think about what each term represents. And we'll build off that as we go. Okay. All right. Any questions on this? Okay. All right. So very quickly before we move on to Navier-Stokes, let me I think the first example everyone always does with Reynolds transport is always mass. But mass, honestly, is probably the easiest application for Reynolds transport. If you were to apply this to momentum, right? Okay. Reynolds transport theorem for momentum does get quite a bit more complicated, and honestly, we don't utilize it all too much for for analysis because of that. The biggest difference is that you can technically produce momentum in a fixed amount of volume. And so the only way that you can do that is by applying an external force, right? And so we basically make use of Newton's second law, saying that if you exert a net external force on an object, that's going to result in a change of its momentum. right? And so when you actually do the mathematics, and so if you took fluids recently, you're probably familiar for this. The production term is not equal to zero for momentum. Okay. In fact, it's equal to the sum of external forces that are being applied to your control point. Okay. So I wanted to just mention that, it's not going to be too important for what we're doing, but it's worth kind of mentioning if we're doing a review of fluid mechanics. Okay. Okay, so that's Reynolds transport theorem, right? The Reynolds transport theorem is applied to control volumes or fixed volumes in space. The other way that we typically analyze fluid problems is to utilize what I call kind of the master equation for fluids, which is the Navier-Stokes equations. Okay. So it's kind of rare, I would say, among kind of scientific disciplines to have kind of like a master equation that everyone tries to solve. Fluid mechanics gets pretty close, and so for most, I would say, practical work with fluids, in engineering and science and otherwise, everyone's basically solving the Navier-Stokes equations, which in concept actually represents the exact same idea as Reynolds transport theorem. It's just in a form that's more general and I would say more general, easily applicable to other forms. Okay. So Navier-Stokes equations, at its heart, basically just represents the conservation of mass and momentum of a flowing fluid. But instead of representing it as an integral equation, we're representing it instead as a partial differential equation. Okay. So in general, partial differential equations are quite common in engineering practice, just because they can be more readily applied to I would say an arbitrary problem, arbitrary geometry. So anytime you can take your physics or your conservation laws and represent it as a differential equation, that's usually a really good starting point. And that's where Navier-Stokes comes in. Okay, so Navier-Stokes kind of has two, well, technically there's four equations, but there's two, I would say, distinct equations, okay? So the first one is the continuity equation, which represents conservation of mass. So the continuity equation is the more simple one. So that's partial u, partial x, plus partial v, partial y, plus partial w, partial z is equal to 0, okay? Where u, v, and w, these represent the x, y, and z components of the fluid velocity field. Okay. So what the continuity equation basically says is that if you take the partial derivative of each velocity with its corresponding direction, you add them all up together, you're going to get 0. Based on conservation of mass. Okay. All right, so that's the first equation. The other equation is generally what people associate with Navier-Stokes, and that's the conservation of momentum part. Okay? So technically, you know, there are three different momentum equations, one for each direction. So there's a momentum equation for the x direction, momentum equation for the y direction, one for the z direction. They all look very similar. And so I'm only going to write out the component for the x direction. But just know that there are two others that look very similar. Okay. Okay. So the Navier-Stokes in the x direction looks like the following. So we have partial u, partial t, plus u, partial x, plus v, partial u, partial y, plus w, partial u, partial z. Okay. So that's the left-hand side. This is equal to -1 over the density multiplied by the pressure gradient. Plus any component of gravity in the x direction. Now, typically, you know, gravity we put in the y or z direction, but if you've rotated your coordinate axes, you know, maybe gravity is in, you know, there's some component in the x direction. But that g can also represent other things as well. It's just gravity is the most common. Okay. And then we have the viscous term. So this is plus viscosity multiplied by the Laplacian of the velocity. So that's partial squared u, partial x squared, plus partial squared u, partial y squared, plus u, plus partial squared u, partial z squared. So this is the equation that typically gives people nightmares and makes people not want to study fluid mechanics. So this is pretty complicated here. Okay. So, you know, we're going to take the same treatment here as what we did with the Reynolds transport. So again, you know, we're not going to be solving any problems with Navier-Stokes. You know, there's a whole class dedicated to that. And even then, you know, we hardly have any time to get to that. But what I'm going to do instead here is to kind of group the terms together. And we're going to basically just talk about conceptually and physically, you know, what they represent and, you know, what effect that has on the fluid. Okay, let me change colors a little bit. Let's use blue. Okay, so first one we have here is the time derivative, right? So that's the only place where the time derivative occurs. So this term here is called the unsteady term. And so what the unsteady term represents is the fact that our fluid velocity or fluid flow is an unsteady phenomenon. So at any point, you know, if you change the conditions, the flow conditions can also change with time as well. Okay. Right. So if you think about, you know, your sink faucet, right? And so if you affix a point, you know, to the nozzle of your sink, right? So the flow past that point can change at any moment. So if you increase the flow of your faucet, you kind of turn the nozzle all the way, or if you kind of just, you know, slow it down, right? Fluid velocity can do the same. So that term represents, you know, the fact that we can have changes with time. Okay. Next one. We're going to group these next three terms together. Okay, so those next three terms represent advection. Okay. So these terms here, you know, conceptually kind of represent the same as the inflow and outflow terms for Reynolds transport, with the fact that, you know, things can be carried along with the flow. So since the fluid flow is moving, things can get carried along with it. Okay. In this particular case, we're talking about fluid momentum being transported with the fluid. which is kind of a trippy thing to think about, right? Because moving fluid has momentum, and so the momentum itself can be transported by the momentum. Um, and in fact, this term here is those advective terms represent the biggest difficulty in solving Navier-Stokes, because it's kind of a nonlinear phenomenon, that the fact the momentum can kind of carry itself to different parts, through the fluid. Um, it's always very confusing to explain, but yeah, later on we'll make some assumptions, and that advective term I think will be a bit more clear. But if you think of this term as similar to the inflow outflow flux terms that we talked about in Reynolds transport, which remember was analogous to our deposits and withdrawals in our bank account, then it starts to make a bit more sense. Okay. Just know that fluid is always flowing, and then things can get flowed, or things get transported along with that moving fluid. Okay, and that's what that term represents. Okay, next we have a single term here, the pressure term. Okay. All right, so technically this is a pressure gradient term because we have the derivative of pressure, but this represents the fact that differences in pressure can drive fluid flow. Okay. Right. So in this situation, pressure plays the role of a forcing agent, something that causes fluid to flow. Okay. That's why it's on the other side of the equal sign. So everything on the right hand side of the equal sign, you can think of those as kind of forcing terms that cause the flow to be altered in some way. Okay. So if you have a pressure gradient, you have a higher pressure in one region and lower pressure in another, that's going to cause fluid to flow, and that's what that term represents. All right, next we have the gravity term. Okay. More generally, this gravity term can represent any kind of body force, and so most commonly that's going to be gravity. So if you're not familiar, a body force is a force that's distributed all throughout the entire volume of whatever object you're looking at. Okay, gravity is the easiest example to think of, just because gravity is just by the fact that within a gravity field, every particle of our bodies feels gravity. It's the same thing for fluids. Okay. The other common body force that you're not going to see all that often in fluids is some kind of magnetic force. And so if the flow is somehow magnetized, you have a liquid mercury or some kind of liquid metal, and you have a magnetic field, that's also going to be a body force. But 99% of the time, that term there represents gravity. And so body forces can drive fluid flow. Right. Right, so that makes sense. And so if you have fluid, if you've ever seen a waterfall, right? And a waterfall is a great example. Waterfall is gravity driving fluid to go from the top of the waterfall to the bottom. Okay, because fluid has mass, just like any other solid object. And so if it's within a gravity field, it will follow or accelerate along the lines of that gravity field. Okay, and then the last term here, these are what we call the viscous terms. Okay, so if you remember on Wednesday, we talked about fluid viscosity. And so viscosity has a very interesting effect, is that viscosity can diffuse momentum throughout the fluid passively. Okay. So those viscous terms actually is something that's not present in Reynolds transport theorem. So in Reynolds transport theorem, one of the assumptions we have to make is that our flow is inviscid. So this is another reason Navier-Stokes is used, because it does incorporate the effect of viscosity, which is very relevant in some cases. Okay. Okay. So that's the Navier-Stokes in a nutshell. And so, eventually we're going to be working our way up to solving this with CFD. Okay. And so it's going to be quite a journey to get there, because Navier-Stokes is not an easy equation to solve. And so, we're going to start with, very simplified versions of this. And then, we'll kind of work our way back up to solving this equation. Okay. Any questions on just any of this so far? Okay, good. Okay. And so if you solve Navier-Stokes, and so like I mentioned before, there are 4 equations, right? So those 4 equations are used to solve for 4 unknown variables, right? And so on the one hand, we have, 3 components of velocity, okay? So those are 3 of the unknowns. And the last unknown is the pressure. And so the idea is that if you are able to solve the Navier-Stokes equations together, all 4 of them, you will have expressions for the velocity, all 3 components, and the pressure. Okay, so 4 equations for 4 unknowns. All right. Now, of course, this equation here is very complicated. And so I kind of very briefly wanted to kind of take a minute to explain why it's very complicated. Okay. All right. So on the one hand, what we have here is a partial differential equation. And essentially what that means is that we have multiple independent variables, right? So we have derivatives in more than one direction, essentially. So we have derivatives in x, y, and z, all 3 components of space. And we also have a derivative in time as well. Okay. Okay. So for the first few weeks, we're going to be working with a very simplified version of this equation. So one of the simplifications that we're going to make is that we're going to assume that, we're not going to have as many derivatives to work with. Okay. All right. So for instance, if we assume the flow is steady, right? So under steady flow basically means that our flow is not going to change with time. And so that's going to eliminate the time derivative. Okay. We can also assume our flow is either 2D or 1D. Okay. And so if we assume 2D flow, right, traditionally we eliminate the z derivative. Okay. Because we're not going to experience any change in the z direction. And then, in the simplest case, if we assume just one-dimensional flow, we're going to eliminate all the y derivatives as well. Okay. So that already eliminates 5 of those terms from our equation, which is a big, big bonus. Okay. Okay. So that's eliminated a lot of the complexity. Another one that we'll be making, at least, for the first half of the semester, is we're actually going to be ignoring the pressure term. So incorporating the pressure into our solution is actually not a trivial task, because pressure behaves actually quite differently from velocity. And so you actually have to have a very specific strategy for dealing with the pressure, called pressure velocity coupling. And so that's something we're going to deal with. We're way not ready for that yet. So that's something we're going to deal with, probably week 9 or 10. And so for the time being, we're going to ignore the pressure just to, help us out with that. Okay. And by doing so, by ignoring the pressure, we also eliminate the need for the continuity equation overall, because the continuity equation is basically the 4th equation that we need to solve for pressure. But if we're ignoring pressure, then we don't need the continuity equation. It's kind of interesting because the continuity equation actually doesn't have pressure at all in it. But when you ignore pressure, the continuity equation is actually the one that gets eliminated. Interestingly enough, but when we do bring pressure back into the fold, you'll see that, the one equation we'll bring back in is continuity. And solving continuity together with the Navier-Stokes momentum equation actually becomes quite complicated. Okay. So after making all of those assumptions, we have a vastly simplified equation from here. So let me go ahead and write it down. Okay. So after applying those equations, we're left with, we still have one term for the advection. So that's u du dx. Okay. Granted, now since we've eliminated all other independent variables, our partial derivative has become a regular derivative. Okay. This is equal to g. Okay. Where remember g represents any kind of body forcing term, plus nu partial squared u partial x squared. These should be d's. I apologize. Okay, we don't have partial derivatives. Yes.
So because we're ignoring pressure, we're ignoring the concept of
Yes.
equation.
Yes.
If we were not ignoring pressure, would that make the equal yes 0?
Yes, technically, yes, because then we keep the continuity equation there, then du dx would be 0, and then you would eliminate that term. But then you would need the pressure term in order to do that. But since we're ignoring pressure, we're also ignoring the continuity equation. Yeah, good observation. That's traditionally what you would do in fluid mechanics, is that you would use the continuity equation to eliminate that advection derivative. Yeah. But we are keeping it for our case. Okay, so this here is a lot simpler. Still a little bit intimidating because we still have a differential equation here, but this seems like it's actually doable. Okay, but there's one more simplification that we have to make, and that's with regards to this term. So this term is notoriously very difficult. And if you ask any mathematician what's the most difficult part of Navier-Stokes, it's this guy right here. It seems very unassuming, right? So we just have velocity multiplied by the derivative of velocity. Okay. But the difficulty with this term is that, because we have velocity effectively multiplied by itself, this is what's called a nonlinear term. Okay. Right? Whenever you have a situation where you have a variable in your equation, a variable that you want to solve for, essentially appears in this form where its exponent is something other than 1, then you have a nonlinear. Okay, it's a little bit hard to see, and honestly, most people kind of miss it the first time they write Navier-Stokes because you have velocity in its plane form multiplied by its derivative. Okay, but if you look at it carefully, right? Essentially, here we have velocity raised to the power of 2 because we have velocity multiplied by its derivative. Okay. And believe it or not, that one small thing actually puts us in a world of hurt in terms of solution methods because, most solution methods that we have for solving differential equations rely on the fact that our equation is linear in our unknown variables. Okay. So if you're getting into the territory of nonlinear equations, then your whole strategy has to really change. And that's true for computations as well. Okay. So we're going to make one final assumption here, okay? And that final assumption being that we're going to assume that the advection velocity is decoupled from the solution velocity. Okay. And so essentially what that means is that we're going to replace one of these velocities with a constant. Okay. Okay. So the change is going to be very subtle, at least, notationally, but, it actually makes a big difference in the equation. Okay. All right. So the big change we made is that we changed that first velocity u into some constant u naught. So this right now is a constant. Okay. And it's been decoupled because before, that u that's in front is the same u that's in the derivative, but now we've kind of changed that velocity in front to be different. Okay. Now what we have here is a linear differential equation, right? Even for 2D problems, if we when we do get to 2D, we're gonna have linear equations, which makes things much easier to solve. Okay. All right. So this is the last version of the equation, or this is our most simplified Navier-Stokes, okay? And this is essentially the one that we're going to be working with over the next few weeks, okay? We are going to go to 2D eventually, and so we are going to add the second dimension, and so that does change things. But in essence, this is the equation we're looking at, okay? In fact, with all of these assumptions here, this equation is honestly kind of barely recognizable from Navier-Stokes. And so, with all these assumptions, we've kind of transformed the Navier-Stokes equation into what's called the general transport equation. Okay. And keep in mind, this is the 1D version of it, because, we've already made the assumption of 1D flow. Okay. And so to kind of make things more general, I'm going to change our solution variable from u to some generic quantity. We'll call it phi. Okay. Okay, so the general transport equation in 1D is u naught d phi dx is equal to gx plus nu d squared phi dx squared. Okay, where phi is some transport quantity. And so the beauty of the general transport equation here is that phi can be actually applied to lots of different quantities. Ironically, except for fluids, because we made that that assumption on the advection, right? But this equation you can actually use to solve for heat transfer. So if that phi there represents temperature, then this just becomes the heat equation essentially. You can also use this to represent mass transfer. So if you have some kind of, like let's say a dye. So you have like a flowing fluid and you inject some dye, then an equation like this can be used to model the transport of that dye through the fluid, okay? So essentially, we've turned our Navier-Stokes equations into like a heat transfer, mass transfer equation. Right? And all of this, all this kind of serves the purpose of making the math, making the theory a bit easier to understand. Because if we work with Navier-Stokes kind of right off the bat, it's a lot of details. It's a lot of things to kind of keep track of once. And so, I wanted to spend a bit of time today, to show you how we can take Navier-Stokes, how we can kind of break it down into something simpler. And just know that this is what we're going to be using. So, this equation, even though it is fairly detached from Navier-Stokes, just because we're kind of sweeping under the rug a lot of the complexities that makes Navier-Stokes. But we have to start somewhere, and we can't really start with just Navier-Stokes because that would just be a little bit too close. Okay. But in the process, even though this class is computational fluid dynamics, you're going to get a little bit of heat transfer, a little bit of mass transfer in this class as well, just because those problems are just easier to solve. Okay. I had friends in grad school that always joked that said fluid mechanics is just heat transfer but harder, which is true when you're talking from a pure mathematical perspective. But heat transfer has, I would say, more difficult applications than fluids. And so I don't want to diss. I am a fluids person by heart, but I don't want to diss the heat transfer people because I also teach heat transfer. So it's like it'd be like I'm dissing myself, which I don't like to do. All right, any questions on this? This kind of concludes our review of fluids. So after this, we're going to start to get into the numerics of finite differences after this. Okay, all right. So that fluids review admittedly was a little bit rushed, but I did want to get through it quickly just because we kind of started with the holiday. So there is a bit more detail in the lecture notes. So there's some detail in there about turbulence. There's some detail in there about initial conditions, boundary conditions, and so those things won't be relevant for quite a while, and so that's kind of why I decided to skip it. But if you are interested, then definitely check out the post in that. Okay, but for the last 20 minutes of class today, I did want to start to introduce the idea of finite differences. And we'll be here in finite differences for a couple weeks, and so this will be kind of our, our launching point here. Okay. So kind of a dramatic shift, right? And so, we spent the majority of today talking about fluids, and so now we're going to shift into numerics. And so, normally I had this, this break here would occur after a lecture, but with the holidays, we just kind of have to keep going. Okay. So finite differences is really interesting, and this when I first learned finite differences, this is where I kind of first fell in love a little bit with numerics because it's a very elegant, very kind of cute way to kind of do numerics. It's kind of the first numerical method I think everyone typically learns, but unfortunately, finite differences doesn't have a lot of practical applications, and so most people nowadays either run finite elements or finite volumes. Finite differences is related to those, but not quite the same. But so its application is a little bit limited. But at least as a learning tool, finite differences is really, really good. Okay. Okay, so what is the idea of finite differences? So the whole idea with finite differences is this gives us a way to take a derivative and essentially approximate it with an algebraic expression. And the way that it does this, I think, kind of is very intuitive. It kind of builds off this idea or this understanding of what a derivative actually represents. Okay, it's very visual. That's kind of why a lot of people use it. Okay, so let's draw a picture. Let's kind of show what this means. Okay, so let's say that we have a curve here. Okay, so let's say that we have x on the horizontal axis, and then vertical axis, we have phi, right? So this could represent our transport quantity, okay? And let's say that our evolution for phi kind of follows a curve that looks like this. Okay. So this curve here represents phi of x. Okay. Some kind of function that has that trajectory. Okay. So the next thing I'm going to do is I'm going to discretize this curve. So let's say that we're going to have, we're going to evaluate the curve at discrete points along the curve. Okay. So I'm going to put a bunch of data points here. Okay. They're going to follow the curve. Right. Let me label these 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. Okay. All right, so we have our curve. Visually, we have our data points here, right? Let's compute something quite simple that normally is quite simple to compute. So let's say that we want to compute the slope of this curve, and we want to do it at a specific location. So let's say that we want to compute the slope of the curve at point number 5. All right, so how would you normally do this? And so if someone gave you a curve and they asked you to find the slope, well, I think the most straightforward thing would be to take the derivative of phi and plug in the x value of where you want to find that derivative, okay? Because, we have the x location here. So let's say that we know that this location here is x5, okay? So to find the slope, okay, you can take your derivative, or you can take your function, take its derivative, right? And then once you have an expression for the derivative, you plug in the x value of where you want that slope 2 to be. Okay? So you take the derivative and you plug in x is equal to x5. Okay? And voila, you have your slope. Okay. Great. So that's in the best case scenario where you have your functions, right? But what if you're in a situation where you don't have a mathematical representation of the function? Okay. So we don't know what the underlying function looks like. All we have is just the image, and we can evaluate the function at those specific locations, right? And so let's say we have, we know the locations for all these. So we know all the x values, right? So we know x1, x2, so on and so forth, okay? And even though we don't know the underlying function, we do know what the value of this function is at those discrete points. So let's say we know phi1, phi2, phi3, phi4, phi5, phi6, phi7, phi8, phi9. Okay. So we don't have the entire mathematical function, but we do know its value at discrete points. Okay. Based on this information, do we have enough here to actually compute the slope? And I would make the argument yes, right? So let's actually go back, think way before, go all the way back to calculus 1. So let's think of or even before that, think of, back to your algebra class, right? So what is the concept of a slope? The slope of a function is how much the slope changes in the vertical direction versus divided by how much it's changing in the horizontal direction, right? So another definition for the slope is essentially how much the function rises over how much the function runs in that same kind of time frame. Right? So essentially, slope is equal to rise over run. Okay. we can compute that based on the knowledge that we have, right? Because we want to compute the slope not as a general function, but we only want the slope at a particular location, right? We only want the slope at location 5, right? So one way we can represent this, and so let me kind of blow up that section here, right? So let's say this is our function here, right? So this is location 5. Its neighbors are location 4 and location 6. And we also know phi 4, we know phi 5, and phi 6. Okay. Okay. So we can compute the rise, right? So the rise in the function, right? The rise in the function is essentially just this amount right here. Okay. And we can compute that amount. So the rise of this function is simply just going to be phi 6 minus phi 4. Right? Because we have the function values at those points. And the run in the same period is going to be x6 minus x4. Right? So the slope of this curve is simply just going to be the ratio of these two quantities, right? So slope is equal to phi 6 minus phi 4 divided by x6 minus x4. Okay. Right? And so that right there, that there is a finite difference approximation of the slope of the curve at that. All right, any questions on this so far? Good. Okay, so let's generalize this. And so, you know, we've kind of derived this expression here for finite difference approximation of the slope, but we did it for a very specific location. But you know, location 5 is nowhere different than any other location there. So, you know, we can make it general in that sense. Okay. Another way that we typically make this generalized is that, you know, typically the way that these grids are formed, right? The spacing in between each successive grid point is usually the same. And so, you know, the horizontal distance between point 1 and point 2, this is usually some grid spacing we call delta x, which is the same as the grid spacing between 2 and 3, which is delta x. Okay. Right. So for the most part, you know, we're going to be working with uniform grids, or at least we are in the theory portion of this class. Okay. And so we can use that to kind of make the bottom a bit more general. Okay. So instead of x6 minus x4, right? So in order to travel that distance, right? So the difference between 0.4 and 0.5, that's delta x. From 0.5 to 0.6, that's another delta x. Just pretend I drew it to scale. They should be the same, right? So x6 minus x4, this should be 2 delta x. Okay. Right. So that kind of makes it more general for any location, assuming that we have a uniform grid. Okay. Now for the numerator, you know, we're basically taking the difference between our two neighbors, right? So we are at point number 5. We took the difference of the function value of our right neighbor minus our left neighbor. Okay. So the way that we make this more general is we can say that, you know, the slope at x is equal to xi is equal to phi I plus 1 minus phi I minus 1 divided by 2 delta x. Okay. And since the slope here represents the derivative at that location, we can say that d phi dx at x is equal to xi is equal to this finite difference approximation. All right, so that equation that we just I just boxed there is what's known as the general central difference equation. Okay, so if you want to find the derivative at a particular point, you take its right neighbor, subtract it from its left neighbor, divided by 2 times the grid space. Okay, it's called a central difference scheme because the differencing scheme is it's centered on the point that we want to find the derivative of. Okay, so we take 1 step to the right, 1 step to the left, find the difference. And then that's our central difference. Okay. All right. Now, the interesting thing about finite difference is that, there's lots of different schemes out there. So, besides central difference, we can come up with other schemes that are represent the same thing, just using a little bit of a different, we call it stencil. And so stencil is just a term that we use to talk about which nodes or which data points are involved in the calculation. Because there will be some situations where maybe we want to involve different data points in our finite different calculations. Okay, because one thing that's kind of funny about the first derivative is that central difference is the one that's typically used, except when we get to things like convection. But the central difference approximation at a location xi actually doesn't involve xi at all, right? So there's no phi I up there. It's phi I plus 1 and phi I minus 1. Okay. So there's other ways to do this. And so what if instead of phi I plus 1, phi I minus 1, we have phi I plus 1 minus phi I. Okay. So we compute our rise by just taking the value of our right neighbor subtracted from our own position. Okay. And since we only moved over one space, we're only going to divide by 1 delta x instead of 2. Okay. So this is another expression for d phi dx at x is equal to xi. Right. So this expression here, since we moved 1 to the right, but we didn't take 1 to the left, we call this our forward difference scheme. Okay. And then similarly, we can do the other way too. So we can take the difference between our current spot and our left neighbor as well. So that looks like this. We have phi I minus phi I minus 1 divided by delta x. Okay. This is another expression for d phi dx at x is equal to xi. Right? And so since in this case, we're only taking a step to the left or we're taking a step backwards, this is known as the backward difference scheme. Okay, so we have three different schemes or three different approaches to do our finite difference. Okay, so how do we choose? Right. So we have three different options here. How do we choose which one is the best to use? Okay, because in most cases, we only need to choose one in order to do our calculations. Right. Well, the answer to that is actually quite complicated because there are situations where we're going to use one scheme over the other. Okay, but at the base level, the criteria or the base criteria that we use is we want to pick the one that gives us the most accurate approximation. Okay. And that's one thing to kind of always remember with these finite difference. And that's one thing that kind of remember throughout the entirety of this course is that, when you do computations, when you use, CFD, you're not solving for a direct solution to Navier-Stokes. You're solving for an approximate solution to Navier-Stokes. Okay. Now that approximation in many cases is going to be very good. It's going to be very close, but at the end of the day, it is still an approximation. Okay. And so in fact, I kind of I just noticed this now. But I kind of mislabeled these equations here. So, when I say that the central difference scheme is this, right, it's not really fair to say that it's equal to, right? What we should be saying is that there should be kind of a squiggly equals, right? So, right, so that represents the fact that this is approximately equal to that. Right? Same thing for the forward difference, same thing for the backward difference, okay? So these finite difference approximations are no greater than that. They're just approximations, okay? And some approximations are going to be greater or better than others. And so when we come back on Wednesday, we'll talk about how we actually assess the accuracy of these approximations, and we'll see which one actually gives us the best representation of the derivative, okay, from a pure accuracy. All right, so thank you everyone for coming today. Hope you guys have a good rest of your day, and I will see you all on Wednesday.
Professor?
We can drop an email. We don't mind, man. Use the same email or I wrote for.
Yeah. I got you. I gave you credit for it. I only answered one, but I gave you credit for one.
So those are all the same.
Yes, exactly.
How did you like say that they're all the same? Like, do you pick the points or?
Yeah, so normally, those points are determined by your mesh. And so if you think about it, when you create your grid on your domain, usually when you create your grid, you're gonna have equals. Yeah, so you basically
And it's always like this?
for the most part. When you have complicated geometries, it does get more complicated because you have to element the store to get. But for now, we're going to assume that's all the same.
Okay, are we ever gonna get it?
We're not going to acknowledge the fact that it happened and then talk about the figure actually. But the calculations are complicated. Yeah.
You're saying how legit.
Hey, what's up? Sure.
I know it's gonna sound very. Assuming 7,
421.
and 475.
Yes.
So they're saying. I guess the file like that, it's certification in the department.
No, those are required classes. You take them.
Yeah, and
right?
I told them apparently that they follow. That it's required.
I think what's happening, so we are changing the numberings on the courses, and so it is messing up things on the TA. Send an email to advise. Do you have the advising email address?
This is for my.
Yeah, but send it to, send email to benefits and then send email to advising. And then we'll confirm that the new number is that you do need 420, because it's weird, in the system, we've changed it, but only halfway, so when on your guys' end, you still see the old numbering, it's 421,407. But in the new number, it's something different, so I think we need to just kind of clear up that confusion with the benefits office, so you do need to be in 407 and 421. You need to get your full benefits, so, it's advising email address is BSME _ advising at Fullerton.edu. Yeah, so go ahead and send an email to benefits and just CC advising, and then we'll clear it up with them to say that, we're going through a numbering change. It doesn't show up on the TDA, but you do need those classes. Yeah,
Sounds good. Thank you, Professor.
yeah, no problem.